I did want to, because you mentioned this, like you have kind of a agent stack on your Mac Mini locally. I have never talked about this before. I actually have not released this either, so I will be releasing something very soon. I had spent a little bit of time. I should be honest and say like this was a kind of spur of the moment project idea that was inspired by something else I'm working on that I can't talk about. Um, but basically, I have been working on this library that's very simple, and it does what I call, I guess, like speculative programmatic tool calling. So the idea is really simple. It sounds complicated. It's inspired very much by like speculative decoding and speculative like execution on a CPU, which for those that don't know, basically it's like when your for CPU, it's like when your CPU is running many instructions, a lot of which might have conditional logic or whatever. Your CPU itself like has a specific like kind of die space dedicated to just executing like things that might not actually happen. And the reason it does this is because like it can afford to. And like it greatly speeds up, like if you have some conditional logic, your CPU might kind of compute it ahead of time. And so when it actually gets to that logic, it will just immediately like have executed. Speculative decoding is somewhat of a similar idea for LLMs, and this is actually used in most of the serving engines that probably you use. I think DSpark is the most recent one that everyone's talking about. But basically, the idea is like language models are very expensive to decode. Like when you decode, meaning you generate new tokens. And so one trick people have used is like you use a smaller model to generate many, many tokens ahead in the time that the big model generates a token. And you effectively use like this importance sampling scheme to make sure that like the small model generations, like you maybe you take like the first three or something, like this scheme falls under the same distribution as if you were just sampling the big model. You know, I think if you're more interested in this, you just read about it. But basically, what this idea is like when your RLM or your code generating agent is generating this program, right? Like it's streaming tokens to generate a program that uses tool calls. So for example, I'm using my sub agent call. This is the example I'm going to provide in this like code base or blog post that I release. When it's generating these tokens, it's in the middle of generating this kind of REPL. It might generate like the subcall like code, right? But it's not done generating the full code. What this speculator will do is it'll queue up this call and it'll start generating the sub agent call early while the main agent is still generating the code. And where this becomes really interesting is when you have loops and conditional logic and all this stuff. We have like I've built, I shouldn't say we, I guess I've built up this kind of lightweight deep copied shadow executor that will like attempt to figure out all the calls inside of your program logic before it finishes generating. And this actually also applies even after it finishes generating. And the reason why I was reminded of this with this Mac Mini thing is the way that this is really useful is obviously like, I mean, you save a lot of time by like calling things before they actually happen. But when you have a local setup with your local agents, one of the things that I'm sure you've run into is like, if you're serving from your like your computer or whatever, and you're using an agent, you're often like memory bound because you just have like the main agent is just generating its sequence by itself. So you have like batch size one. Um, and you have to wait for it to finish before it launches whatever subagents it needs to do. Versus in this case, you immediately queue up the subagents. So you're actually like utilizing more of your GPU, I guess, or your compute. And you're probably still memory bound, but you're less memory bound than you used to be. And so this kind of trick gets you like basically free speedups. Like I think I've just ran this like on a local setup that replicates a lot of the RLM paper, and I can speed up the main experiments by like 2x. And it's mainly just like really simple. Like it's like a really simple thing. It just happens like especially when the like your serving engine is not or whatever your tool calling engine is not like fully utilized. But also, you just save the time for the main context. And so, yeah, like, this will come out pretty soon. It's a neat thing. It's not actually really a researchy thing. It's kind of just this implementation that I've also just added to the RLM repo. And it'll be public probably by the time this podcast is out. But yeah, it's super exciting. I think it's I'm excited, especially for people that do like local stuff, like locally running agents. Like I think this is it actually should also work with your regular coding agents, like if you use Prime Agent or other things. But I have to implement, I have to make sure that I actually interface that well. But yeah, yeah.
Yeah, I mean, it's such a powerful idea. It's so exciting. Our last podcast, I talked to Matthew Jacob, who's working on Trace Lab
Mm,
at UW, and yeah, this idea of a serving like VLLM, but for agent execution. That's kind of like how I'm thinking about it. I'll give one other shout out to Jack O'Brien and Subconscious,
mm.
a part of the Boston area, Cambridge AI group, and they're doing this kind of like yeah, like run times for agent execution. And then my question to you with this is, because I'm also interested in this kind of like, we have like effort tiers and we have like, we're doing agents for search, and it's like, routing between like, cause you do this sort of like planning ahead, and then you could have like a prediction of which of these paths do I need to take. Are you thinking about that with this? Cause you have this speculative execution where you're imagining these different scenarios, but then it's like, oh, what if I put a predictive layer on top of that to
Yeah.
cut? Yeah.
Yep. So the way that it's currently implemented is like super simple in that like there is very little prediction, right? Like it's almost like if you can parse it and it's all literals, like you run it. If you have a safe path of execution, now a big part of this is like because you're executing code twice almost, like you want to make sure anything you do is not mutating other stuff. So there's a lot of rules in the current implementation of this that like it basically makes it so it's safer, right? But I agree with you that ultimately what we want to do is be more aggressive, right? With speculation. Now I don't have time to work on this because I think this is a real problem. Like this could span like a whole line of research, which I want it to. This is why I'm kind of proposing this, because I think like there's a lot of work that can be done in this direction. And if nobody does it, I'm happy to do it, in due time, I guess, when I finish up all the other things I need to do. But with like, if we really lean into this code execution angle, right? One of the things we want to make sure that happens is like there are a lot of bottlenecks in code execution, especially where in the case of an agent, we have a lot more information. And what I mean by this is like typically with code execution, you rely on the compiler to deal with everything. But the thing is with LLM generated stuff, we have more information than a compiler would. Because, for example, we know how expensive certain tool calls are. Or we also have this prior that, like I said before, if you're using sub agents, we know that we want to increase, sometimes we want to increase the serving load of whatever like LLM calls we're doing. And so we would rather batch a lot of these things together inside of our serving engine than wait for them to happen like in the course of the code execution. Because the code execution can be really long. Like for all we know, we don't know if it's short or long. Um, and so like I am very excited by like there is a limitation for what I'm doing, which is that there are many unsafe operations, and the shadow REPL or whatever refuses, or the speculator refuses to execute them because we don't want things to happen. But you could have a language model look at the code and say like, I predict this call is going to happen. Even like, and there's no way of knowing this otherwise. And this would be super powerful. Like I think there's a lot of really cool stuff you can do. And I should actually probably also look at what Trace was it Trace Labs or Trace is doing. I think one thing I should also say which I'm not working on. So I invite anyone to work on this. I think modern serving engines are mostly built for, again, serving like these legacy designs of language model, chat model type things. They do work very well for agents, but they're not designed for agents. And I think one thing that people should start thinking about is like, is there is there something else we can design specifically around agents that really takes advantage of what the agent is actually doing? Because right now, all serving engines treat all language model requests as equal. Right, like it probably doesn't even distinguish between them. Like when you do like this, like actually, that's a lie. Maybe at Anthropic or OpenAI, in when they have specialized serving engines for Claude Code or Codex. I don't actually know. I would believe that, but I think at least in the open, like everybody relies on these open serving engine stacks, which are purely designed for just independent language model requests. And so I think this is something that's going to be very interesting moving forward, especially for locally running agents as well. Like if you want to serve everything on your end, right now, like it's often not worth it from the perspective of like, are you fully utilizing your GPUs? The answer is probably no. And so like I would be very interested in seeing if people design systems around this as well.